Welcome back to the last lecture of Module 4 on specification and verification on code. I'm Rustan Leino, and in this lecture we're going to take a look at sorting. So there are many sorting algorithms, and today we're going to study just a simple one of them, and that will give you more of a feeling for what invariants are and how you use them and how you use the invariants to reason about the code. So let me remind you, we're using Daphne. Daphne is a programming language that was designed with reasoning in mind, and it has features like arrays and loops that we will need for the example. It also has specifications built in, like in the Eiffel programming language, and we will be able to write loop invariants directly in the language. It has a verifier that runs in the background and that will check our work. If you have not installed Daphne already, here are two links where you can do that from. You can either run Daphne in the web browser at the Rise for Fun link, or you can install it on your own machine. And if you do that on your own machine, you can do it on any platform using one of the 3 IDEs, and that will give you a more interactive experience as you go through and learn and write code and specifications. Okay, the sorting algorithm that we're going to take a look at is called the Dutch national flag algorithm, and it is the inner loop, if you will, the inner workings of the quicksort algorithm. And at that point, it's often called the pivot algorithm because you're sorting a pivot, and the pivot gets sorted between all of the other elements. But this can be represented as the Dutch national flag, which has colors as shown here. And what we're going to do is we're going to imagine that we have an array of 3 colors. Some of the elements are red, some are white, and some are blue, and we're going to sort them in that order. So in the flag here, it's going from up to down. So the array that we're given then has a bunch of elements, and each element has one of these 3 colors. That's what we're going to focus on. And the way that we're going to sort them is that we're going to keep around 3 different variables, and the 3 variables are going to segment the array as the following picture shows: R, W, and B. And what I'm showing you in this picture is really the loop invariant of the Dutch national flag algorithm. That is, this is the invariant that describes what we're trying to achieve with the loop. And as you can see in the picture, we're going to arrange that at any point in the loop, all of the elements to the left of R are going to be red. All of the elements from R to W, and again, since we're using half open intervals, what that means is from the index R up until less than the index W. But if you think of them as markers between the elements like this, then it's just between R and W. All of those elements are white. And then in the upper end of the array, we have that all of the elements above the B marker are blue. And then there's that region in between that is here a pale green, and those are the elements that we have not yet visited. So of course the goal is to shrink that region down to nothing, and at that point we are done. Let's take a look at the code. Let's write the code for the Dutch flag. We will start by introducing some values for the colors. To do that, I will introduce a type, an enumeration type, and called color. And an enumeration type is just a special case of an inductive data type, which in Daphne is declared as follows. The values can be red, or white, or blue. Those are the 3 values. Now we need to have some way of comparing the colors, and I will think of them as being from left to right, and therefore red is going to be less than white and blue. And I will include a function for doing so. I'll call it below, and by below I mean less than or equal. So in other words, this is going to allow the inclusive comparisons. That is, it's going to be reflexive. Red is going to be below itself, for example. And it's going to take 2 colors as a parameter, and it will return a Boolean. Well, you could do it this way, which is fine, but often when we speak about these things, a function that returns a Boolean is often called a predicate, and you can call it that in Daphne if you'd like. They're synonymous. So what does it mean for a color for C to be below D? Well, here you can think about any kind of representation of these that you'd like, but I'll just write it as follows, and you can check my work to make sure that you think that this is indeed the predicate we want. I will say that C is below D exactly when either C is red, then the below always holds, or if the two colors are equal, or if D is blue. And those are the three cases. And again, you can go through that in your mind to make sure that it is correct. Daphne will let you prove some theorems or do some examples with that, but we're not going to bother with that at this point. But of course, it's crucial that we get this part right, because if we don't get this predicate right, we're going to sort according to some comparison metric, that does not make sense. Okay, so the method we're going to write then is the Dutch flag, and it will take an array, and the array in this case is going to be an array of colors, and we're going to sort it. Now, to give us permission to change the elements of the array, we need to include that as part of the specification. So I will write a modify specification, which says we are allowed to modify the elements of the array. In other words, if someone calls this method, they should not expect that the elements are the same as they were before. That is, some changes may have occurred among the elements of the array, but other objects and arrays are not modified by the method Dutch flag, but we need to include it here. Okay, what is the specification then going to be? The post condition is going to say, we saw a similar specification as a precondition to binary search. We're going to say that for all indices that are in indices into the array, the A sub I is below A sub j. Again, where below is that predicate that we defined up there. So that's what we'd like to ensure as that's the sortedness part of the post condition. So let's get started from this point to write the code for doing so. And as I showed in the slide, we're going to have three variables, R, W, and B, and we're going to initialize them as they were on the slide. So since we have not yet looked at any kind of element in the array, both R and W are going to be at the left extreme, so both are set to 0, and B is set to the whole length of the array. That is, it's going to be the bound just to the right of all of the array elements. So we're going to have a loop, of course, and here we're going to continue looping while that green region existed on the slide. So the green region was between W and B. So as long as W is strictly less than B, that is, as long as there's some space between W and B, we're going to continue looping. And as we have seen now in several examples, we're going to write an invariant about the variables that change in the loop, R, W, and B in this case. And I will write those as this, and you can see how nicely these line up. And this is a good part of the documentation for what we're intending to do in the loop. Okay, so how are we going to make sure now that everything is sorted from here? Well, what we'd like to record as part of the invariant is that those three regions, the red region, the white region, and the blue region, that they are the colors that we have said. So I will write them. I'll use quantifiers in this case as well, even though I've hinted at before that there are other ways that you could do this in Daphne that will look simpler, but since we're using quantifiers here, I will just continue showing you with those. So all indices that are to the left of low, all of those array elements are to be red. All of the indices from low to, what am I doing? Low. Of course, I meant R. From R to W, all of those elements are white, and all of the array elements from B on upwards all of them are blue. Okay, that is our invariant. And by just writing down, what did I do here? Okay, actually, first of all, I made a mistake here. We would have found that later, but that's not what it's complaining about. But okay, so oh, that is what it's complaining about. Initially, the other one would not have held, so we did discover that error. Okay, that's good to have the verifier run as we're trying to write the program, so we can find mistakes as soon as possible. Okay, this is our invariant, and you can see that actually we're not getting any complaints about the post condition. So in this case, that suggests that these invariants are what we need, or at least along the way to proving the post condition. But of course, as we're getting the warning about, we have not yet written the loop body. We've just given like a specification of the loop body. But in fact, for a program like this, writing down the invariant is the most difficult part. Once you have a clear idea in your head, just as we saw earlier with the Fibonacci program or with binary search, once you have a clear idea in your head what the loop is supposed to do, it's not difficult to write the loop correctly. So that is what we're now going to do. So inside the loop, we're going to inspect one of the elements because we're going to sort the next element. And the green region where we have elements lies between W and B. So we're going to take one of those elements. And it's natural to just look at A sub W, which then is the leftmost element of that green region, the region of elements that we have not yet sorted. In this case, I can, because the type is a data type, I can do a match, which is sort of like a case. And we will have three cases here. We have red, we have white, we have blue, and we're going to have to do something in each case. All right, what do we do in this case? If the first element of the green region is red, we'd like to move that down. Let me remind you on the slide. So we have an element that we're looking at here in the first part of the green region, and we're finding that it's red. So we'd like to move that element here to extend the red region. But of course, there's a white element here that's already in that location. So we need to take that white element and move it to this element. So in effect, what we're going to do is we're going to swap this element here with the element here. So let's see how that translates in the code. So we're going to change the array element at A sub R and at A sub W. And we're going to in fact swap these two elements. Once we've swapped these elements, we also need to update the pointers, the R and W pointers. And for both of those, what we're going to do is we're going to move each one of those one step to the right. Okay. All right. So what happens in the white case? Well, the white case is a simple one. If the next one that we're looking at is already white, we don't need to change the array at all. All we need to do is we need to advance the W pointer, and we do that as such. And then finally, in the blue case, if we find a blue element in that region, what we're going to do is we're going to swap we'd like to move it close to the blue regions, which means that what we would do is set the element like that. But we must remember we don't want to just overwrite that element. We had better do something with the element that was there previously. So we will in fact do another swap of that as well. And once we've done that, we need to move B down, but we don't do any change to W. And you can see that that is correct. We're getting no complaints. So we've just written a sorting algorithm for these three colors. But there's one more thing that is typical of sorting algorithms when you specify them, and that is that we want to make sure that the output elements are the same as the input elements. Often that is phrased as the output should be a permutation of the input, which I think is an unfortunate wording because it makes you think from a formal perspective, it makes you think of trying to formalize what permutations mean, and that can get quite hairy. all we want to do is say that the elements in the array in the output are the same as the elements in the input. And we can specify that in Daphne as well. So let's write another post condition for that. And I've left this to the end because as we will see, it will be pretty simple to ensure that it holds, and then means we can think about the other complaints, verification complaints first, and then add that. Okay, so we'd like to talk about the elements of the array. How do we do that? Well, in Daphne, you can convert you can take the elements of an array and convert it into sequence. A sequence is a value type in Daphne. And so we can do that by by specifying a range of elements. So we'll go from 0 to a dot length. So what I've written here is an expression denoting the sequence of elements in this range. And of course, as we have seen before, this is a half open interval, so it goes from and including 0 to but excluding a dot length. So well, turns out if the lower bound is 0, we can omit it because the default lower bound is 0. And also if the upper bound is the length of the array, we can omit that. And in this case, we're omitting both, which looks really strange when you see it, especially the first time, but that's a bit shorter. So what I've written here is an expression denoting the sequence of elements in the array. Now we want to say that sequence of elements is contains the same elements as in the pre and post states. So of course, the sequence itself is not going to be the same because we are permuting, we are changing the elements in the array. So I would like to have the multiset of these elements. So a multiset, in a set, you just count each element once, regardless of if there are duplicates. But the multiset also keeps track of the duplicates. So what we'd like to say is that the multiset of elements in the post state of the array are the same as the multiset of elements in the pre-state. So to get to the pre-state elements, I will use the old keyword, which says evaluate this expression in the pre-state of the method. So here I'm saying that the multiset of elements in the array in the post state should equal the multiset of the elements in the the multiset of elements in the post state should equal the multiset of elements in the array from the pre-state. Okay, so that's the other part of the post condition that we'd like. And here it's pretty simple because this condition, of course, it holds initially because then the current value of the array is just what it was in the old state before we have started changing it. And with every case where we're changing elements in the array, which is this place here and this place here, what we're doing is we're swapping elements. So in fact, this condition that we have is going to hold at with every iteration of the array if we interpret this as the current value. So I will just add that invariant, and I'll just copy and paste it down here, and that's all. We're done. This now also proves that that in the post state we have the same elements as we started with, and we're proving that by keeping that as an invariant with every loop iteration. So that was easy enough. Okay, so as an assignment for you, I'd like you to do a simpler sorting algorithm, simpler than the one with 3 colors, and it is to sort an array of booleans. So there you just have 2 values, and you can sort them in a similar way, and include as the specification the parts that it is sorted and that the elements don't change. Of course, with 2 elements like that, there are different special cases that you could consider for the sorting algorithm. Sort in the way that you think is pleasing, and make sure that you verify it as well. That's your assignment, but if you feel especially ambitious and would like to continue the fun, you could also try a version of a Dutch flag algorithm that uses not 3 colors but 4 colors, and the ideas will be the same. You will have more regions in the array, but there will be more cases, and you should be able to do that in a similar way. If you feel up to that, I encourage you to do that as well, but your assignment is to do the sorting with the Boolean array. So thank you very much for listening to these lectures. I hope that you've learned things about pre and post conditions, and I hope that you've learned things about invariants, and we've looked at loop invariants in particular. These are important concepts in software engineering and for writing code, making sure that it is correct. And it also ties in with verifying the code. They're the same sorts of things that you need if you want to verify the code, as we can do with a verifier like Daphne, as we have seen. So good luck with that, and as always, program safely.